Hey, hey, hey! It's Dr. J. We're moving on to section 2.3 today. It's quite a title, Solving Equations Using the Subtraction and Addition Properties. So we're really getting into it now. So first thing I want to mention is equations. Slightly different than an expression. An equation is a mathematical sentence with an equal sign. Okay. And we think of equality, we assume that equality actually means equal. Right? Because you can't solve an equation if you're not at least buying into the concept of equality. Equality is sometimes represented as some scales, something like that. So you have, A is equal to B, and we assume that these are actually equal to each other, like scales. In other words, they have the same value, they have the same weight, they have the same meaning. They are equal to each other. I have to get rid of the title so I can actually do some math here. One way to think about it something like this. All right, come on back to me. Don't stop me now. So while I'm waiting for this thing to calm down and come back to earth here. Come on, come back to earth. There we go. So one thing I want to mention throughout the lesson today is that when I say something like A or B, when I use these capital letters, I'm talking about the entire left-hand side of the equation, So when I say A, I mean everything that's on the left-hand side. I sometimes abbreviate that LHS. Yeah. And B, I mean everything that's on the right-hand side. I call that RHS. RHS, okay. I try not to use lowercase letters. Some people do. In fact, I think the book probably does, is lowercase a and lowercase b. Now, that can be confusing because you might think of those as variables. And so I'm really not, when I'm talking about the left side and the right side of the equation, I'm really not talking about variables per se. I'm talking more about placeholders. So this A sort of represents the entire left-hand side. So I'm assuming that these two things are equal. And so one way to think about it is you can think of the balance scale, sort of balancing the two sides, right? And so this line down the middle that I'm drawing really represents the equality, all right? It's just the line of equality. So this is the right side of the scale, and this is the left side of the scale. Or this is A, and this is B, yeah? And we're assuming that A and B are equal on the balance scale here. So one way to think about an equation is using a manipulative. So you can think of X as sort of a mystery box, yeah? Yeah. Or sometimes they'll think of it as an envelope. If anybody's read the book, you have some envelope that's sealed, and you don't know what's inside the envelope, okay? But you do know that you have 4 objects that you're adding to it. Okay, so you have some mystery envelope, that's your X. Yeah, you don't know what it is. You have 4 objects. We sometimes refer to these as tokens. And then we know that that's equal to 12 objects. Okay. Again, tokens, objects, you can think of them as coins. Although if they are coins, they all have to be the same coin. So they're all pennies, or they're all nickels, or they're all pennies are probably the best thing to think about. And so in order to solve an equation like this, we could think of subtracting these and make sure that you subtract the same amount. From both sides, yeah? So I'm basically canceling out all of these tokens here. Yeah. I'm taking away 4. You can think of just literally removing them from the scale and removing them from the scale. And then you would get that the envelope, yeah, because you've gotten rid of all the tokens, is equal to however many tokens are left. Yeah, so it looks like how many are left? 8. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 tokens left. And so we would say that x is equal to 8. So that's an abstract way of thinking about what it means to solve an equation. All right. Now, I tell you what, I'm never going to do this again. All right, I only do this once in this class, and that's it. That's just sort of give you the sort of, manipulative way of thinking about what does it mean when I actually solve an equation. Could you imagine every single time I need to solve an equation, I have to draw this box, and I have to draw the envelope, and I have to draw these tokens and things like that. So we have a much more efficient way of understanding this concept. So this concept can be summarized with a property. Yeah, this is called the subtraction property of addition. I'm sorry, the subtraction property of addition. The subtraction property of equality. That's what it's called. The subtraction property of equality. And so what it says is if A is equal to B, that's, again, left-hand side is equal to the right-hand side. Those are those sides of the scale. Then A minus C is equal to B minus C. And we call this the subtraction property of equality. In other words, if you subtract the same value from both sides, the equality is preserved. Yeah, you have preserved the notion of equality. You haven't damaged it. You haven't thrown the scales off balance. In other words, the scales will still be balanced. That's what we mean by preserving equality. So throughout this lesson, throughout the rest of the chapter, and in fact throughout this entire course, our goal is to preserve equality. We're trying to keep the equality intact until we start solving inequalities. And that's a whole nother story. But as long as we're talking about equations, our goal is to preserve the equality. All right. So that's your introduction to solving equations. Let's go ahead and do some examples. X plus 5 is equal to 21. All right. Now, I'm again going to do this one time. The left-hand side is the A. Yeah, that's your A. and the right-hand side is your b. This is the beginning of the, the story here, so I'm keeping the equations relatively simple. All right. And now what I'm going to do is I'm going to subtract c. There's your c. C is typically the number that you're trying to get rid of. Those are those little tokens that I was talking about. And I'm just going to draw it like that so it's very clear. So again, I'm not going to do this every time. I'm only going to do this once. I'm going to say A minus C, so C is the 5, is equal to B minus C. That's here. So the minus C is what we often call the constant. Yeah. There are other symbols that represent constants, but C is very common. Okay. So now I have plus 5 and minus 5 cancel. The x has been isolated. All right, so we're trying to get the x by itself. And then now we have 21 minus 5, which is 16. Okay. Not too bad, huh? Let's try another one. Q is a terrible letter for now. Now, I said I was only going to do this once, but why don't I do it one more time? So now A is 9. A is the left-hand side of the equation, and B is m plus 3. And so my constant is going to be the opposite of 3, because your goal is to isolate the variable. All right. So again, I'll just write this one time here. I'll say A minus C is equal to B minus C, you see? So A is 9, and C is minus 3. That's minus C. And then B is all of this, m plus 3. And then C is the minus 3. And that's the last time I'll do that. Okay. In general, we just say 9 minus 3 is 6. Positive 3 and negative 3 will cancel out. And from now on, we will not write the A, B, and C. Okay, the A, B, and C are abstract concepts that I like to use to get the ball rolling, to kind of get you into the mood. And then at one point, we're going to abandon these, and we're just going to solve the equations. So this is the way you'll do it in practice. Here's the way you'll do it in practice. So you'll just think, oh, this is A, and you'll think this is B, but you won't actually write it. Okay. Now, why do we even bother saying that? Because the key is, who is C? C is always the opposite of whatever you're trying to get rid of. So you're trying to isolate the Y, so C is negative 9. That's your C. All right. So in my brain, I'm thinking of that as being the C. That's the constant that I'm moving. We typically draw a line here just to keep track of our steps. We cross off the 9s and the negative 9s. We bring our equal sign down. We usually scoot our variable over, and then we do the math. So 17 minus 9 is 8. Okay. So that is the subtraction property of addition. The subtraction property of equality. Next, You know, I've been thinking about addition this whole time. That's why it keeps coming out. The addition property of equality. It's very similar. It says if A is equal to B, then A plus C is equal to B plus C. This is what I call BOGO, or buy one, get one free. If you memorize the subtraction property, you get the addition property for free. Or vice versa. If you memorize the addition property, you get the subtraction property for free. All right, so let's go ahead and solve x minus 7 is equal to 13. So again, I'm not going to write it, but A is everything on the left-hand side. That's A. B is everything on the right-hand side. And then C is the thing that we are going to introduce. We are going to add the C. So the C is the 7. Yeah, so I'm adding 7. So that's the plus C. I like to add it underneath. If you have room, you can actually add it off to the side. Yeah, typically when we write the property, we do it sideways, but when you actually do it, you do it vertically. And you cross these guys off, scoot your variable over, bring down your equal sign, and then add these up, and you get x is equal to 20. All right. As the equations get more complicated, I'll probably encourage you to check them. I think today we can skip that. Otherwise, we'll be here for more than an hour. But you can just mentally check it. 20 minus 7 is 13. Check. All right. I'm not going to make a big deal about that now, but as the equations get more complicated, I will definitely start making a big deal about checking their answers, especially because I screw up all the time. So, I mean, the other day, I multiplied two numbers and totally got the wrong number, and just went right on past it. So checking is not a bad idea. All right, example 5. Oh, and there goes my camera. Somebody who invented autofocus thought they were doing us a favor, and they're really not. I've turned off the autofocus, and it just still wants to stay on. So come on back to me. Come on back to me. All right, so 13 equals p minus 6. All right, p is the variable. You want to get p by itself. So we're going to add the opposite of negative 6. So we're going to add positive 6 to both sides. That's our C. Yeah. And then you're going to add these up, and you're going to get p is equal to 19. All righty. So that ought to do it. Let's do some applications. Geometry. In particular, we're going to be finding the missing side. All right, find the missing side. So it's really just one application, but I'm going to do multiple versions of it. So suppose I have a triangle. Yeah. And I know that this side is 8, this side is 10, and this side is A. Let's find the missing side. If the perimeter 24 units. Find the length of the missing side. All right. So I've got 24 units. So again, the perimeter, we've talked about this before. Perimeter means outer measure. So we're going to add up all of these sides. And the perimeter is 24 units. I'm just going to generically say units at this time, but eventually we'll have inches and centimeters and feet, and that's a whole nother topic we'll talk about later. So for now, I'm just measuring this with generic units. All right, so there's our perimeter equation. Okay. And then we have 10 plus 8 is 18. I'm trying to get A by itself. So I'm going to do the opposite of 18, which is negative 18. I'm adding or subtracting. Either way you can think about it. Subtracting and adding are basically the same property. Crossing these guys off. Scooting my board up a little bit. I get A is equal to 6. So there you go. A is equal to 6. Try another one. If the perimeter of a rectangle is 214 units, and the length is 82 units, find the width. So you might want to look at a picture here. So you have a W and L. Now, if I turn it up right, then I would say W would be this side and L would be the other side. It really doesn't matter. I know the length is 82, so I'm just going to get rid of the letter L. Remember, I'll give you a hint. We should never have more than one letter in a problem. Not in this class, yeah, or at least not yet. Not in this chapter. All right. And then I'm adding up all the sides, yeah. Well, I want to show you something. In a rectangle, the perimeter is all the way around, all four sides, yeah. But if you just take two of the sides, 82 plus W, this is called the semi-perimeter. The semi-perimeter is half of the given perimeter. So the semi-perimeter is 214 divided by 2, which is 107. So now we have 82 plus W is 107. That's called the semi-perimeter. Semi means half. Yeah. Semi-perimeter. Make sure you do that because you don't want to put 214 here. That's too much. So you have 82 plus W is 107. I'm running out of room here, so I don't know where I could scoot over here, I guess. So I've got 82 plus W is 107. I'm going to subtract 82 from both sides. And I'm going to get 25. Double check that. I've screwed this up before. 7 minus 2 is 5. 10 minus 8 is 2. So I get 25. So the width is 25. These are tricky. Let's try another one. Hopefully I'm not getting too blurred out here. Let's see. Really can't control my blurredom. The perimeter of a parallelogram is 196 units. Remember what a parallelogram is. It's like a tilted rectangle. These lines do have to remain parallel. Forgive my drawing. It's not perfect. I'm going to go ahead and call this one W. And I'm going to call this one 54. And then I also have the height of the parallelogram, which is 50. And I intentionally do this with parallelograms. I sometimes will do it with triangles too, where I'll put an internal height, but I'm telling you about the perimeter. Yeah. So since I'm talking about the perimeter, since this is not outside, you can ignore it. Very important. All right. If we were talking about area is the inside, then we would need that 50. The 50 would become important. But we're not talking about area today. We're talking about perimeter. So I use the same exact diagram when we talk about area. So you might wonder, well, why don't you just take that away? Well, because I want to use the same picture when we eventually get to area. All right, which is, I mean, it'll be a little while till we get to that. I guess we have talked about area a little bit, right? Just not in this context. Okay, so we want the semi-perimeter. The semi-perimeter is 2 of the sides. The semi-perimeter is 196 divided by 2, which I think is 98. I did that in my head. You might want to check that. Yeah, it is 98. Yeah. Okay, so our equation is going to be W plus 54 is equal to 98. That's the semi-perimeter. And then you're going to subtract the 54. And you're going to get W is 44. 44 generic units, whatever those units happen to be. All right. Hopefully I'm not going too fast. This is the very beginning of solving equations. As the equations get more complicated, I'll certainly do less examples and slow down the train a little bit. Feel free to pause, rewind, whatever and I'm sure I don't need to tell you that. You're all going to. Okay? All right, so next we're going to talk about translating. This will be our last topic today. I do a lot of word problems in this class. Funny thing is this is one of the beginning level classes, and I don't hold back with the word problems. I basically do word problems as often as I possibly can. All right. We've already talked about all the different words that translate from English into math. Now we're just going to be practicing this. All right, so example 9. 3 more than a number. 3 more than a number is 12. I'm going to give you credit for 2 different parts of this. One is the translation. So just writing this as an equation. For all of these examples, we're going to use x as the variable. So whenever you see a number, that's going to be x. All right. So I've got 3 more than. More than means plus. Is, keyword there is. So look for the word is, and then 12. Okay. And since addition is commutative, commutative means you can change the order. This is also correct. I don't need both. All right, it's your choice. You want to say 3 plus x, or you want to say x plus 3. Either way, it's fine with me. I actually like the x plus 3 myself, because next you're going to solve the equation. I almost screwed that up. I wrote 13. 12, 12, 12. Double check everything's 12. All right. I prefer to solve it this way, although you will get the same answer if you solve it this way. Subtract 3 from both sides, and x is equal to 9. All right, so you have 2 possibilities for the translation. I'll accept either one. Remember, I like to say tomato. I also like to say tomato. Example 10. Five less than a number is 16. Find the number. All right, less than. Less than means subtract. Yeah. A number means x. 5. Now, subtraction is not commutative. Yeah. Which means that if you put this in the wrong order, if you put 5 minus x, this would be incorrect. All right, that would not be correct. So don't do 5 minus x. You must do x minus 5. All right, must be in this order. So there are no tomatoes and tomatoes when you're talking about subtraction. Subtraction, there's only one way to do it correctly. So it must be x minus 5. Look for the key word there. The key word is is. That's your is. And then 16. So the translation is x minus 5 is equal to 16. Now we're going to solve this. Add 5 to both sides. And the solution is 21. I'm not going to make a big deal about it in this class, but at some point I might have to. At least I'm not going to make a big deal about it in this lecture, but the solution is technically just the number. Yeah, it's just a little semantics of mathematics. We don't say the solution is x equals 21. That's not the solution. This is just another equation. Yeah, this is what we call an equivalent equation. So you want to be the life of your next party, or you want to be loved and hated at your next family get-together? Yeah, I'm taking algebra in college. Yeah, and you know, x equals 21 is not the solution. No, it's not. The solution is 21. X equals 21 is what we call an equivalent equation. All right. But I would have to be a real jerk to mark that wrong if you said it wrong, or perhaps, suppose we were back in school someday, in the year 2023 or whatever, we go back to school, and I start collecting your papers again by hand, and you wrote this when I really wanted you to write that. I'm not going to do that, really. I just want you to get the right answer. There are other versions of this problem. You could say the sum So I could say the sum of a number and 13 is 25. So again, sum means addition. A number, we might as well just use X. You can use other letters when you're doing this on your own. My homework is programmed to only, at least for these problems, to only accept X. Okay. All right. The sum of a number and 13 is 25. I like to sort of dial it in that way. And then you have choices. You can say 13 plus X is 25, or you could say X plus 13 is 25. Either one. It's up to you. Notice you get the same answer either way. X equals 12. If you do it over here, minus 13, you're still going to get X equals 12. Yeah, same answer. Because addition is commutative. Again, I don't expect you to do the problem twice, but I do want you to know that when you have an addition problem, so sum or more than or something like that, you can do it either way and you should get the same answer. But that's not true for subtraction. The difference of, or sometimes we'll say the difference between so the difference between, all right, must be written in this order. A number goes first, and 9 must go second. It must be in this order. All right, because subtraction is non-commutative. So if you write it backwards and it's subtraction, you will always get the wrong answer every single time. There's not one instance where it works both ways. And then 38, look for the key word there, is, and is 38. All right. And then we're going to add 9 to both sides. X is 47. Eventually, we're going to solve more complicated equations. So I'm going to end this lesson with a couple equations that I'm just kind of introducing so that you can see what's coming down the road. And then I'm not going to solve them. Translate, do not solve. Twice the sum of a number and 6 is 11. twice the sum of a number and 6 is 11. So twice means the same thing as double, which means the same thing as multiply by 2. The sum of a number and 6. We're actually going to do that first. All right. Then you're going to multiply it by 2, but you have to use parentheses. All right. Because it doesn't say twice a number. It doesn't say that. It says twice the sum. And that means that the 2 is applying to the entire sum. All right. Now, I don't want you to solve this. Just leave it in this form. All right. Then look for your keyword, is, and then clearly 11, and then you are done. We will solve this equation in a future section. I can't tell you right now. It'll screw up my whole plan. So, if you already have had algebra and you want to solve this for your own peace of mind, you might not like what you get. You might get a negative number. You might get a fraction. You might get stuff that I haven't really talked about yet. So that's the reason why I'm not going to solve it. But you feel free to solve it if you really want to know. Okay. I also don't want you simplifying it or anything like that. Okay. I think we can handle one more. Four less than twice a number. So now we are saying twice a number. So no parentheses. It really does take practice to learn how to speak math, right? I mean, if I say twice the sum, well, then you have to use parentheses. If I say twice the difference, then you have to use parentheses. But if I just say twice a number, you can just say 2x. All right. Or you could say 2.x, but I'm not requiring the dot. All right, then remember we've talked about this, 4 less than. So that's going to go down here, minus 4. Might as well use all my colors today. Is, I've been waiting to use this purple pen. I don't know how purple shows up on, probably just looks like blue, is 7. So there you go. And when you check your answer, you just read it back to yourself. 4 less than twice a number is 7. Yeah. Notice in math, we do not always read from left to right. We sometimes bounce around and read, you know, the way you might read a magazine at the doctor's office or something. I mean, you don't always start on the first page, do you? I don't. I sometimes just flip right open to the middle, you know. Sometimes I read it backwards. I don't know. I'm just waiting for my appointment anyway, so. All right. I hope you all enjoyed this. Until next time, I'll see you on the internet.